Hi everyone, and welcome to my talk on how to apply loop subdivision in real time using the formalism of mesh half-edges. So this is work I did with my colleague Jonathan, and we're both from Unity Technologies. So first, let me recall what subdivision surfaces are. They are algorithms that define how to obtain a refined surface given a coarse one, with certain guarantees of smoothness of this refined surface. And this is very useful in video production and games, as it allows to create, manipulate, store, stream, etc. a lightweight mesh, and compute and visualize a smooth and detailed surface at render time. Subdivision surfaces are calculated by repeatedly applying local rules that cut each geometric primitive into smaller ones. Here you see the two most popular rules, Catmull-Clark and loop subdivision. One of the problems is the exponential growth of primitives with subdivision depth, as you can see here. And yet it remains crucial for modern applications that this subdivision happens in real time, even on large meshes. Here you see a live demo of our result, in which we'll achieve subdivision up to 5 million faces in just a few milliseconds. So this is definitely within real-time frame rates. Now, what's the state of the art in fast subdivision algorithms currently? Well, until recently, this was called feature adaptive subdivision and was invented about a decade ago. It allows for real-time evaluation of an important part of the subdivision algorithm, enabling a rendering of complex meshes. And as you can see in this demo, it even allows animation with real-time evaluation of the refined surface points. However, this relies on a pre-computation that actually happened prior to the recording of this demo, and is valid only when the mesh topology remains static. If I reevaluate the full end-to-end subdivision, which I've actually triggered here in the demo, we see that it takes a long time. Actually, the demo is now still frozen, and it will take about 20 seconds to compute the end-to-end subdivision. It will soon pop with the refined result. Well, this was the exact same setting as the slide before with our technology. Now, why is this so slow? Well, it is because feature adaptive subdivision functions in two steps. The second part, this one, evaluates the limit surface in a parallelizable and efficient manner. But it can do this only using pre-computed tables that evaluate local patches, respecting some topological constraints. And therefore, the first part consists of a slow pre-process that cuts the initial mesh into patches, and may even have to preemptively refine some of them locally. And this is what took 20 seconds in the demo just before, and has to be recomputed at each change of topology. So as a result, while rendering of static topology can be real-time, mesh editing with live visualization of the refined surface cannot. There are two very recent works that do obtain real-time end-to-end subdivision. Mlakar and colleagues' paper introduced a groundbreaking mesh representation using large sparse matrices. These are tailored for fast downstream subdivision kernels on the GPU, hence achieving real-time performance end-to-end, even for mesh editing. Yet their data structure is quite uncommon and definitely non-standard yet, so this may hinder adoption. And therefore, we have proposed last year a completely different approach that achieves similar performances using the more common Halfedge mesh formalism. However, we designed it specifically for Catmull-Clark subdivision, and what we're doing today is extending this to loop subdivision. So in our work, we're going to propose a new way to evaluate loop subdivision by exploiting the underlying half-edges that structure the mesh. And it relies on the observation that under loop subdivision, a half-edge, for example this red one, can be written as to always split into 4 new ones. And we will show that this can give rise to a computation of the refined topology and geometry in a parallelizable manner. Now let's see how we leverage these half-edges to obtain this result. First, let me introduce the half-edge mesh formalism we use. A mesh is encoded using 2 buffers, the half-edge buffer describing the topology and the vertex buffer containing the geometry. The latter is all you're used to, 1 entry per vertex and giving the 3 coordinates of each vertex. The topology buffer, on the other hand, stores each half-edge one by one as an entry, and for each entry it gives the following information. The ID of the twin half-edge, which is gives a way to fetch this half-edge, the opposing one along the edge, from a half-edge, its next and preceding half-edge within a face, the ID of the vertex it sits on, the ID of the edge it spans, and the ID of the face it lies in. Now let's look at an example. This configuration here, which was tagged with the different IDs of the structural elements, is stored by this table. So here we see for half-edge entry number 0, which is the red one here, H0, we have a twin number 11, that's this half-edge. We have a vertex ID number 0, and an edge ID number 4. So that's what's stored in here. And note that given that we are dealing with triangle-only meshes, 3 operators need not to be stored, as they can be defined analytically and are universal. It's these 3. They essentially mean that within a triangle, 3 half-edges are numbered consecutively. And as such, the half-edge buffer is a superset of a common index buffer. Yet this also means that when subdividing the mesh, we'll have to take care to keep these analytic relationships valid at all times. So now that we've defined the mesh representation, how do we apply a step of loop subdivision? The loop subdivision rules are known, and they tell us to split each triangle into 4 new ones. For example, this orange one splits into these 4. And to assign new geometric values to the vertex points of the refined configuration, following a local interpolation of the old vertex points, given a formula that is defined by loop subdivision and that I'm not giving here. So in practice, we need to do 2 things. Define the refined topology by populating a new half-edge buffer for this configuration, and similarly, populating a new geometry, a vertex buffer, for this configuration as well. And therefore, we define exactly 2 algorithms to fulfill these respective tasks. But very crucially, we wish to enable doing this in parallel over half-edges. And therefore, our algorithms both run over half-edges, and we'll later see how to parallelize over it. Let's dig into the topology algorithm. Each half-edge of this configuration, when processed, needs to write all attributes of its 4 succeeding half-edges. For example, so this red one needs to write all the attributes for these 4 new ones, and it should start with assigning an index number, so an entry in the new buffer. We decided that half-edge h will split into half-edge indexes 3h plus 0, plus 1, and plus 2, so that's h0 gives h0, h1, and h2, and an additional 4th half-edge at the end of the buffer, so numbered at the end, here 117 in this case, and it's the half-edge that will come and compose this central triangle. One of the reasons we did this particular construction is because it preserves the analytic formula here in all cases and for any subdivision depth. Here you can see that although these 3 came from 3 different half-edges that were processed individually, their numbering is consecutive. So next we assign the twin, edge, and vertex attributes using a list of analytic rules. This is given in our algorithm here. I'm not going to detail them, but essentially they guarantee consistency in the subdivided half-edge buffer while minimizing the amount of operations to do here in the algorithm. And they're composed of simple lookups, geometric combinations, and lookups of topological information. The second algorithm creates the refined vertex buffer. Remember, the loop subdivision rules assign an interpolated value to each new vertex point, and our algorithm iterates over half-edges, and thus processes each half-edge individually. And we therefore make each half-edge, when processed, scatter a partial contribution to the new vertex points. Let's look into more specifics here. We have 2 types of vertex points. Here you see an edge point. So that's a new point that comes and splits an old edge into 2. Its new position is a weighted combination of these 4 vertices, the 2 along the edge and the 2 opposing ones. So we make these 2 half-edges, when processed in our algorithm, scatter a weighted contribution of these vertices to the location storing this new vertex point's coordinates. So for example, when the green one is processed, it fetches these green vertex points, weighs them, and scatters an additive contribution into the location where this vertex coordinate will be stored. And that's exactly what happens in this line here. Similarly, when the red one is processed in this same loop, it will fetch these two, weigh them, and scatter its value here as well. The second type of vertex points point is a vertex point, an old vertex point that gets a location that is updated following the one ring of vertices around it. So here we make all these half edges, the outgoing ones from this old vertex point, contribute to the value, the coordinate of this vertex point here. So as such, by going over each half edge and summing all contributions, we obtain the new positions that follow the loop subdivision rules. Both algorithms can be parallelized over half edges, and we provide two implementations of this. One using OpenMP parallel for loops on the CPU, so that's simply replacing the for loop in each of these algorithms by a parallel for loop, and one using compute shaders in OpenGL on the GPU, so that's essentially writing one shader per algorithm and running each shader once per half edge. One thing that should be taken care of is that there are incremental writes to the same data in these lines of the algorithm. So this can be dealt with using atomic add operations that ensure consistency. This may in turn slightly slow things down, but the number of concurrent writes remains limited to a handful, and we will see that this remains pretty efficient. So regarding results, here there is a first graph that essentially shows our main achievements. It says that half-edge parallelization over half-edges is effective and scales well. So what we see here is that every line gives the performance, so the runtime performance, when parallelized over a varying number of threads. 1 thread, 2 thread, 4, 8, etc. on a logarithmic scale. And we can observe that the processing times decrease linearly with the amount of CPU threads used, and get minimal when using the massively parallel GPU. So we can conclude that there is very little interference between threads and that parallelization scales well. And this thus allows us to compute end-to-end subdivisions of large meshes of up to 100 million subdivided vertices in real time on the GPU. In our case, it was an NVIDIA GTX 2080. We've also compared against the Open Subdiv library, which is an open source library that is used, that is an industry standard, that is used by many modelers in the industry, and it actually implements feature adaptive subdivision. We've compared in two scenarios. First, a rendering scenario in which topology is considered fixed, and we only need to evaluate the geometry. So this is the exact scenario Open Subdiv was built for. No expensive pre-computation of patches is necessary here. And in this context, Open Subdiv and our method have on-par performances. On this particular mesh, Open Subdiv outperforms our method slightly, but this varies and cancels out across meshes. The second scenario is a modeling scenario in which topology can be modified. In this case, Open Subdiv resorts to its expensive pre-computation, and logically our method is orders of magnitude faster. All these evaluations have been done extensively over a set of meshes that you see here, with varying complexities and subdivision depths, and by analyzing the timings for all subparts of our processes, for example, for all compute shaders. So this is all available as a supplemental material. There are many pages like this with a lot of results in it. You can look it up with this QR code. One thing that I completely silenced in this presentation is that we handle crease tags, which are the yellow lines, the yellow edges on these depictions. These are edges that the mesh author can tag so as to forbid smoothing at sharp edges, which can be a useful feature to have for industrial applications. And this actually gives rise to a third algorithm that we execute, but this was all included in our timings already and doesn't change anything to our conclusions. I just wanted to mention that we handled them. So finally, I'd like to conclude by summarizing our contribution and restating that with this paper, we've extended the class of parallelizable and real-time subdivision algorithms to loop subdivision and making it applicable to dynamic topologies, including the handling of crease tags. Note that code is fully available for download, so feel free to look that up. The code actually implements not only loop subdivision, but also Catmull-Clark subdivision of our last year's contribution. And finally, regarding limitations and future work, please note that we have solved the problem only for uniform subdivision, so no adaptive subdivision at all. And that we believe it may be possible to improve cage coherency and maybe gain some performance on that side. So I'd like to thank you for your attention, and I'd be happy to take questions, whether online or offline, depending on when and where you're looking at this presentation. Feel free to drop me a note or a question if you want to. Thank you very much for your attention. Goodbye.